Hello, my dear students. Welcome to ESR chemistry classes. Here we are in lecture number 2 on ESR spectroscopy, which is an important topic in inorganic spectroscopy. Let us start our discussion with a spin magnetic moment of electron. The spinning electron produces a magnetic moment which is called a spin magnetic moment or simply a spin moment. The spin magnetic moment of the electron is directly proportional to its spin angular momentum. That is, greater the spin angular momentum of electron, greater will be the spin magnetic moment produced by it. The spin magnetic moment produced by the spin angular momentum of electron can be given by the following relationship. Mu s, that is a spin magnetic moment of electron, is equal to minus g into E by 2 MEC into H by 2 pi into under root S into S plus 1. We have already seen in the previous video that H by 2 pi into under root S into S plus 1 is nothing but the spin angular momentum of the electron, and it is obvious that the spin magnetic moment of electron is directly proportional to the spin angular momentum of electron, and this term may be regarded as the proportionality constant. This equation can be written as follows: mu s is equal to minus g, and these two terms written in red words can be combined together as beta into under root s into s plus 1. Here beta is equal to E by 2 MEC into H by 2 pi, that is EH by 4 pi MEC, and this term is known as Bohr Magneton, which is abbreviated as BM. Here the term G is called G factor. It will be discussed in detail in coming videos. E is equal to charge on electron, Me is mass of electron, C is velocity of light, H is Planck's constant, and S is nothing but a spin quantum number of electron. This is the expression for the spin magnetic moment produced by the electron. Calculation of the value of Bohr Magneton. It is the unit of magnetic moment. We have already seen in the previous slide that 1 Bm is equal to Eh by 4 pi MEC. On putting the values of constants involved in this equation in CGS system, we have E, charge on electron, is equal to 4.8 into 10 to the power minus 10 ESU. The value of Planck's constant is 6.626 into 10 to the power minus 27 arg second. 4. The value of pi is 3.14 and mass of electron is equal to 9.109 into 10 to the power minus 28 gram. and the velocity of light is approximately equal to 3 into 10 power 10 centimeter per second. Thus, we have put the values of constants in this equation in CGS system. On solving this, we have 1 bm is equal to 9.27 into 10 power minus 21 arg per Gauss. This is the CGS unit of magnetic moment. In SI system, in international system, 1 bm will be equal to 9.27 into 10 power minus 24 joule per Tesla. Try to convert this value of Bohr Magneton from CGS system to SI. This is a homework. It will be seen in the classroom. 1 bm is equal to 9.27 into 10 power minus 21 arg per Gauss or 9.27 into 10 power minus 24 joule per Tesla. The negative sign in this equation, mu s is equal to minus g into e by 2 pi mec into h by 2 pi into under root s into s plus 1 indicates that the magnetic moment vector, a spin magnetic moment vector of electron is in the opposite direction to that of a spin angular momentum vector. This negative sign indicates that the spin magnetic moment vector and the spin angular momentum vector are in the opposite directions. This is the nucleus of atom. It is a spinning electron are spinning in the anti-clockwise direction, and it is the direction of a spin angular momentum vector of electron. The spin magnetic moment vector of electron acts in the opposite direction to the spin angular momentum vector. A spin angular momentum vector of electron and a spin magnetic moment vector of electron act in the opposite directions, and this fact is reflected by the negative sign in this equation. The term G in the above equation for magnetic moment of electron is called Lande's splitting factor or G factor of the electron. It will be discussed in detail in incoming videos. For free electron, the value of G is equal to 2.0023. This is the value of G factor for free electron. The value of G of electron in atom, molecule or ion changes with the change in chemical environment. The value of G for free electron is equal to 2.0023, but in atoms, molecules or ions, the G value of electron changes with change in chemical environment. Interaction of a spinning electron with external magnetic field. Two spin states of electron. We have already seen that ms is equals to plus 1 and ms is equal to minus half. These are two spin states of electron and these have the same energy. That is, are degenerate in absence of external magnetic field. Let us see it again. Two spin states of electron, ms is equal to plus half and ms is equal to minus half have the same energy, that is are degenerate if there is no external magnetic field. But when an electron is placed in external magnetic field of strength B and interaction takes place between the spin magnetic moment of electron and the applied magnetic field. If a spinning electron is placed in an external magnetic field of strength B and interaction takes place between the spin magnetic moment of electron and the external applied magnetic field, and as a result two spin states of the electron, that is ms is equals to plus half and ms is equals to minus half, remain no more degenerate and they split up. And this splitting up of two spin states of electron in an external magnetic field is called Zeeman effect. The energy of any spin state of an electron in an external magnetic field is given by the following relationship, and it is E is equal to G beta B ms. This is the energy of any spin state of the electron in the presence of external magnetic field of strength B. We know all the terms: G, G factor, beta, Bohr Magneton, B is the strength of external magnetic field, and ms is magnetic spin quantum number of the electrons, which can have value plus half or minus half, and E is the energy of any spin state of the electron. It is obvious that the spin states ms is equal to plus half and ms is equal to minus half of electron will have different energies in the presence of external magnetic field of strength B. The energy of electron with alpha spin, that is ms equals to plus half, is equal to G beta B into, this is the value of ms plus half, and it is equal to 1 by 2 G beta B, and the energy of electron with beta spin, that is ms is equal to minus half, is equal to minus 1 by 2 G beta B. This is the energy of electron with alpha spin, and this is the energy of electron with beta spin. In other words, the spin states of electron will split up into two energy levels in an external magnetic field. Zeeman splitting of electron spin levels in external magnetic field has been represented diagrammatically below. The energy is increasing in the upward direction. These are two spin states of electron. ms is equal to plus half and minus half, and these two spin states of electrons have the same energy in absence of external magnetic field. This is a spin quantum number of electron, s equals to half, and these two are magnetic spin quantum numbers of electrons, plus half and minus half, and these two spin states of electron have the same energy if there is no external magnetic field. But when external magnetic field of strength B is applied, the energy of electron with beta spin, that is ms is equal to minus half, will be equal to minus 1 by 2 g b beta. On the other hand, the energy of electron with alpha spin, that is ms is equal to plus half, will be equal to plus 1 by 2 g b beta. And the energy difference between these two spin states is equal to delta E is equal to G B beta. This is the energy difference between two spin states of electron in the presence of external magnetic field of strength B. If electromagnetic radiation is incident on a spinning electron in the presence of external magnetic field, the electron will absorb energy equal to G B beta, and it will undergo transition from ms is equal to minus half, that is from beta spin to alpha spin. When the sample containing unpaired electron placed in an external magnetic field is exposed to the electromagnetic radiations, the electron absorbs EMR having energy equal to delta E, that is G B beta, and the electron undergoes transition from lower energy spin state, that is ms is equal to minus half beta spin, to higher energy spin state, that is ms equals to plus half, that is alpha spin. When the sample containing unpaired electron is placed in an external magnetic field and it is exposed to electromagnetic radiation, the electron absorbs energy equal to delta E, that is G B beta, and it undergoes transition from lower energy spin state to higher energy spin state, that is from ms equals to minus half to ms equals to plus half, that is from beta spin to alpha spin. It is said that resonance of electron spin has taken place. Under this condition, we can say that resonance of electron spin has taken place. The resonance of electron spin from beta spin to alpha spin has taken place. It is called electron spin resonance. The resonance of a spin of electron from beta spin to alpha spin, and the absorption spectrum obtained in this way is called electron spin resonance spectrum. The resonance of electron spin will take place only when the resonance condition is satisfied. Let us see what is the resonance condition. The energy of electromagnetic radiation absorbed must be equal to the energy difference between two spin states of electron. The energy of EMR is equal to h nu. The energy of electron with alpha spin, that is higher energy, is 1 by 2 G beta B, minus the energy of electron with alpha spin. We have already seen that it is minus 1 by 2 G beta B. On solving, minus minus will become plus, and h nu will be equal to G beta B. This is the energy of electromagnetic radiation, and this is the energy difference between two spin states of electron, and under resonance condition the energy of electromagnetic radiation must be equal to the energy difference between the two spin states of electron, and the value of frequency of EMR absorbed under resonance condition is equal to G beta B divided by H. Here, nu is the frequency of EMR absorbed during the resonance of electron spin. During the resonance of a spin of electron from beta spin to alpha spin, EMR is absorbed and its frequency is nu. It is obvious that the energy difference between two spin states of the electron, that is delta E is equal to G beta B, depends upon the strength of the applied magnetic field. The energy difference between two spin states of electron, that is delta E, which is equal to G beta B. This energy difference depends upon the strength of the applied magnetic field. The applied magnetic field is kept generally of the order. In ESR spectroscopy, the strength of applied magnetic field is generally of the order 3000 Gauss. Under this condition, nu is equal to G beta B by H can be solved by putting the values for free electron. Nu is equal to, this is the G value for free electron, 2.0023 into, this is the value of beta, 9.27 into 10 to the power minus 21 arg per Gauss, and the value of B is 3000 Gauss, and this is the value of H, 6.626 into 10 to the power minus 27 arg second. On solving this equation, the overall unit will be per second, and it is equal to 8.4 into 10 to the power 9 per second. This is the frequency of EMR absorbed during resonance of the spin of free electron in an external magnetic field of strength 3000 Gauss. Thus, when applied magnetic field has a strength of 3000 Gauss, the resonance of free electron takes place by absorbing EMR of frequency 8.4 into 10 to the power 9 second, which falls at the borderline of microwave region and radio wave region. This frequency falls at the border of radio wave region and microwave region of the electromagnetic spectrum. We can simply say that the ESR spectrum, that is electron spin resonance spectrum, is obtained in the microwave region of the electromagnetic spectrum. To attain resonance condition, the resonance condition, we have already seen that the resonance condition is H nu is equal to G beta B. That is the energy of electromagnetic radiation to be absorbed must be equal to the energy difference between two spin states of electron in external magnetic field, and this resonance condition can be satisfied by varying frequency of microwave or by varying applied magnetic field strength. This resonance condition can be satisfied in two ways. The first method is to vary frequency of electromagnetic radiation, keeping a strength of applied magnetic field constant. And the second way is to vary the strength of applied magnetic field, keeping the frequency of microwave radiation constant. But in actual practice, the ESR spectrometer operates at a certain frequency, usually about 10,000 gigahertz. 1 gigahertz is equal to 10 to the power 9 hertz. Therefore, 10 gigahertz will be equal to 10 to the power 10 hertz. That is 10 to the power 10 per second. In actual practice, the ESR spectrometer operates at a certain frequency of microwave, and this is usually 10 to the power 10 per second, and the resonance condition is satisfied by varying the strength of applied magnetic field, usually in the range 3000 to 4000 volts. The value of B is varied from 3000 Gauss to 4000 Gauss, which is equal to 0.3 Tesla to 0.4 Tesla. Please note that 1 Tesla is equal to 10 to the power 4 Gauss. It is obvious that to attain this resonance condition, the frequency of microwave is kept constant and the strength of applied magnetic field is varied from 3000 Gauss to 4000 Gauss. Use of equation h nu is equal to g beta b. The above equation has three variables: nu, g, and b. Beta is constant, h is also constant, h is Planck's constant, and beta is Bohr Magneton. These two terms are constant, but this equation has three variables: nu, g, and b. If any two of these three variables are given, if any two of these three variables are given, the third quantity can be calculated using this equation. Let us illustrate it with the help of a self-assessment problem. The ESR spectrum of methyl free radical is observed at 330 millitesla in a spectrophotometer operating at 9250 megahertz. Calculate the G value for the electron in methyl free radical. Let us see it again. The ESR spectrum of methyl free radical containing one unpaired electron is observed at 330 millitesla in a spectrometer operating at 9250 megahertz. Then we have to calculate the G value of electron in methyl free radical. Let us see. 330 millitesla is equal to 330 into milli means 10 to the power minus 3, and 1 Tesla is equal to 10 to the power 4 Gauss, and it is equal to 3300 Gauss. This is the value of B, and the frequency is 9250 megahertz, and we know that 1 mega means 10 to the power 6. This is 9250 into 10 to the power 6 per second, and it is equal to, in the standard form, 9.250 into 10 to the power 9 per second. This is the value of nu and this is the value of B. Then we have to calculate the G value for electron in methyl free radical. Here is the solution. It is the resonance condition. We have to calculate the value of G. G is equal to h nu by G. This G should not be present here. We have already written G here. G is equal to h nu divided by beta b. On keeping the values of these terms, h is equal to 6.626 into 10 power minus 27 arg second into nu 9.250 into 10 to power 9 per second. The value of beta is 9.27 into 10 power minus 21 arg per Gauss, and the value of b is 3300 Gauss. All the units will be cancelled out in the numerator and denominator, and there will be no unit of G. On solving it, we have the value of G for electron in methyl free radical equal to 2.0035. Please note that this value of G for electron in methyl free radical is different from that of free electron, which is equal to 2.0023. The value of G for free electron is 2.0023, but the value of G for electron in methyl free radical is 2.0035, and this change takes place due to change in chemical environment. Now, two problems have been given here for homework. Please solve these problems and submit the copy of your answer in the classroom for evaluation. Here is the first one. At what magnetic field strength would methyl free radical come into resonance in a spectrometer operating at 9.5 gigahertz if the G value is 2.0026? At what magnetic field strength would methyl free radical come into resonance in a spectrometer operating at 9.5 gigahertz if the value of G of electron in methyl free radical is 2.0026? We have to calculate the value of B, that is the strength of applied magnetic field. Calculate the frequency of EMR absorbed during resonance of an electron from ms equals to minus half to ms equal to plus half. This should be plus half. During resonance of electron from ms equals to minus half to ms equals to plus half in a magnetic field of a strength 0.35 Tesla. In this problem, we have to calculate the value of nu. Please solve these two problems and submit your answer in the classroom for evaluation. Thank you for watching the video with concentration. Please like, share and subscribe it so that you may get information regarding my new videos in time. We will meet shortly in lecture number 3 on ESR spectroscopy. Thank you again.